National Electrical Code Section 408.3b specifically addresses high-leg delta systems. The code explicitly states that a high-leg delta system shall not be used to supply a single-phase 3-wire circuit in which the neutral conductor is connected to the grounded conductor. Understanding the implications of this code section is crucial for ensuring electrical safety and preventing potential hazards when working with high-leg delta systems. A high-leg delta system, also known as a wild-leg or stinger-leg delta system, is a type of three-phase electrical service where one phase winding of the transformer is center-tapped and its center tap is grounded. This creates a system with two phases providing the standard 120 volts to neutral, while the third phase provides a higher voltage, typically around 208 volts, to neutral. This higher voltage phase is the high leg. The primary reason for prohibiting the use of the high leg to supply a 208-volt single-phase load with a grounded neutral is to prevent voltage imbalances and potential damage to equipment. In a properly balanced three-phase system, the voltage between any two phases should be equal. However, when a single-phase load is connected between the high leg and the neutral, it creates an imbalance. The voltage between the high leg and neutral is significantly higher than the voltage between the other two phases and neutral. This imbalance can lead to overheating of conductors, malfunction of connected equipment, and even fire hazards. Furthermore, many single-phase loads are designed to operate at a specific voltage, typically 120 volts or 240 volts. Connecting a 208-volt single-phase load to the high leg and neutral would expose the equipment to an overvoltage condition. This can damage the equipment's internal components, reduce its lifespan, or cause it to fail prematurely. The grounded conductor, also known as the neutral, is designed to provide a return path for current in a single-phase circuit. It is typically connected to the center tap of the transformer winding and is intentionally grounded at the service entrance. When a single-phase load is connected between the high leg and the grounded neutral, the current flow is not balanced across all three phases of the system. This can lead to excessive current flow in the neutral conductor, which can overheat the conductor and potentially create a fire hazard. To illustrate the potential dangers, consider a scenario where an electrician mistakenly connects a 208-volt single-phase air conditioner to the high leg and neutral of a high leg delta system. The air conditioner's compressor motor is designed to operate at 208 volts. However, due to the voltage imbalance caused by a high leg connection, the motor may experience an overvoltage condition. This can lead to overheating of the motor windings, damage to the motor's insulation, and eventual motor failure. In addition, the unbalanced current flow in the neutral conductor can cause the conductor to overheat. This can melt the conductor's insulation, create a short circuit, and potentially start a fire. To prevent these hazards, it is essential to follow the NEC guidelines and avoid using the high leg to supply a 208-volt single-phase load with a grounded neutral. Instead, alternative methods should be used to provide power to such loads. One option is to use a separately derived system, such as a transformer, to create a dedicated 208-volt single-phase supply. A separately derived system isolates the 208-volt load from the high leg delta system, ensuring that the voltage remains balanced and the neutral current is properly managed. Another option is to use a three-phase transformer to convert the high leg delta system into a standard three-phase system with a balanced voltage. This allows for the safe and efficient supply of both three-phase and single-phase loads. It is also important to note that the NEC requires specific labeling and identification of the high leg conductor. This helps to prevent accidental connections and ensures that electricians are aware of the potential hazards associated with a high leg delta system. The high leg conductor is typically identified by orange coloring or other approved means. In addition to the NEC requirements, it is crucial to follow safe work practices when working with high leg delta systems. This includes using appropriate personal protective equipment, such as gloves and safety glasses, and verifying the voltage of each conductor before making any connections. It is also essential to have a thorough understanding of the electrical system and to consult with a qualified electrical engineer if there are any questions or concerns. The consequences of violating NEC Section 408.3b can be severe, ranging from equipment damage and personal injury to legal liability. Therefore, it is imperative that all electricians and electrical contractors are aware of this code requirement and adhere to it strictly. Furthermore, regular inspections and maintenance of electrical systems are essential to ensure that they are operating safely and in compliance with the NEC. This includes checking for loose connections, damaged wiring, and any other potential hazards. In summary, NEC Section 408.3b prohibits the use of the high leg over high leg delta system to supply a single-phase, 3-wire circuit in which the neutral conductor is connected to the grounded conductor. This rule is in place to prevent voltage imbalances, equipment damage, and fire hazards. By following the NEC guidelines and using alternative methods to supply 208-volt single-phase loads, it is possible to ensure electrical safety and prevent potential disasters. Firstly, understand the purpose of the grounded conductor. Secondly, recognize the dangers of voltage imbalance and equipment damage. Thirdly, learn alternative methods for supplying 208-volt single-phase loads. Fourthly, always follow safe work practices and consult with qualified professionals. Ignoring these precautions can lead to serious consequences. Remember, electrical safety is paramount. The high leg delta system is a unique configuration that requires careful attention and adherence to the NEC. By understanding the code requirements and following safe work practices, it is possible to work with these systems safely and effectively. The NEC is a comprehensive set of standards that provides guidance on the safe installation and maintenance of electrical systems. It is updated regularly to reflect the latest technological advancements and to address emerging safety concerns. Electricians and electrical contractors should stay up to date on the latest NEC requirements and incorporate them into their work practices. In addition to the NEC, local codes and regulations may also apply. It is important to be aware of and comply with all applicable codes and regulations. Continuing education and training are essential for electricians and electrical contractors to maintain their skills and knowledge. This includes learning about new technologies, code changes, and safe work practices. By investing in continuing education, electrical professionals can stay ahead of the curve and provide the highest level of service to their customers. The electrical industry is constantly evolving, and it is important to adapt to new challenges and opportunities. This includes embracing new technologies such as smart grids and renewable energy systems, and developing innovative solutions to meet the growing demand for electricity. By staying informed and embracing change, electrical professionals can contribute to a more sustainable and efficient energy future. In conclusion, NEC Section 408.3b is a critical code requirement that must be followed to ensure electrical safety when working with high leg delta systems. By understanding the dangers of using the high leg to supply 208-volt single-phase loads with a grounded neutral and by following the NEC guidelines, it is possible to prevent voltage imbalances, equipment damage, and fire hazards. Remember, electrical safety is everyone's responsibility. The NEC is not just a set of rules, it is a guide to ensuring the safety of people and property. By following the NEC and promoting a culture of safety, we can create a safer and more reliable electrical system for all. The importance of proper grounding cannot be overstated. Grounding provides a path for fault current to return to the source, which helps to protect equipment and prevent electrical shock. The NEC specifies detailed requirements for grounding electrical systems, and it is essential to follow these requirements carefully. Overcurrent protection is another critical aspect of electrical safety. Overcurrent protection devices such as circuit breakers and fuses are designed to interrupt the flow of current in the event of an overload or short circuit. This helps to prevent damage to equipment and reduce the risk of fire. The NEC specifies the appropriate size and type of overcurrent protection devices for different types of electrical circuits. Wiring methods are also an important consideration when designing and installing electrical systems. The NEC specifies the types of wiring methods that are permitted for different applications, and it is essential to use the appropriate wiring method for each situation. Proper wiring methods help to ensure the safety and reliability of the electrical system. Electrical equipment must be properly listed and labeled to ensure that it meets safety standards. Listing and labeling indicate that the equipment has been tested and certified by a recognized testing laboratory. This provides assurance that the equipment is safe to use and will perform as intended. The electrical inspections are an important part of the electrical safety process. Electrical inspections are conducted by qualified inspectors to verify that electrical installations comply with the NEC and other applicable codes and regulations. Electrical inspections help to identify and correct potential hazards before they can cause problems. Electrical safety training is essential for all electrical workers. Electrical safety training provides workers with the knowledge and skills they need to work safely with electricity. This includes learning about electrical hazards, safe work practices, and the proper use of personal protective equipment. Electrical safety audits can help to identify potential hazards and improve safety performance. Electrical safety audits are conducted by qualified auditors to assess the effectiveness of an organization's electrical safety program. Electrical safety audits can help to identify areas where improvements are needed and to develop strategies to reduce the risk of electrical incidents. A comprehensive electrical safety program should include policies, procedures, and training to ensure that all electrical work is performed safely. A comprehensive electrical safety program should also include regular inspections, maintenance, and testing of electrical equipment. By implementing a comprehensive electrical safety program, organizations can create a safer working environment and reduce the risk of electrical incidents. The NEC is a living document that is constantly evolving to reflect the latest technological advancements and safety concerns. It is important to stay up to date on the latest NEC requirements and to incorporate them into your work practices. The electrical industry is a vital part of our economy, and it is essential to ensure that electrical work is performed safely and reliably. By following the NEC and promoting a culture of safety, we can create a safer and more prosperous future for all. One final point. Always consult the latest edition of the NEC and any applicable local codes before performing any electrical work. These codes are the minimum safety standards and must be followed to ensure the safety of people and property. Also, remember to disconnect power at the source and verify it with a meter before working on any electrical components. The absence of voltage must be verified, even when a circuit is switched off, to ensure it is truly energized.